A river of gas longer than our entire galaxy flows silently through the void. This is not science fiction, but a real cosmic structure known as the Magellanic Stream. It is one of the most profound mysteries in our galactic backyard, and by the end of this journey, you will understand how this river in space is reshaping our most fundamental ideas about the universe. We will uncover what this colossal river is made of, how it reveals the invisible hand of dark matter, and where its ancient currents are ultimately carrying it. What forgotten story does a river written in hydrogen tell about the past and future of our own home galaxy? It was a whisper in the static, a ghostly signature etched into the radio waves. During the 1970s, astronomers were meticulously mapping the sky with new radio telescopes, instruments that could see the faint glow of cold hydrogen gas invisible to optical telescopes. What they found was not a neat collection of stars or galaxies, but something far stranger. Stretching across a vast arc of the southern sky was an immense, tenuous filament of gas. It appeared to flow from two of our closest galactic neighbors, the large and small Magellanic Clouds, and curve gracefully toward our own Milky Way. They called it the Magellanic Stream. To grasp its scale is to confront the sublime. This river in space is not merely large, it is almost incomprehensibly vast. From its headwaters near the dwarf galaxies to where it seems to pour into our own, it spans nearly 300,000 light-years. Picture that for a moment. A single light-year is the distance light travels in 1 year, moving at 299,792,458 meters every single second. This river is 300,000 times that length. It is so long that if you could lay it across our galactic disk, it would stretch from one side to the other and then keep going far beyond. It is, without question, one of the single largest structures in our entire local group of galaxies. Yet for all its staggering size, the Magellanic Stream was profoundly mysterious from the moment of its discovery. Its very existence posed immediate and profound questions. Where did all this gas come from? A river needs a source. Was it torn from the Magellanic Clouds by the Milky Way's gravity? Or was it the remnant of an even older, more violent encounter? And why did it look so pristine, a smooth ribbon rather than a scattered cloud? The gas was cold and quiet, not hot and turbulent as you might expect from a violent collision. It was as if the universe had painted a perfect, delicate brushstroke across the cosmos and left no explanation for the artist's technique. This beautiful, silent serpent in the dark demanded a story, and finding that story would lead astronomers to confront forces they could not even see. This river is not made of water, but of the most fundamental ingredient of creation itself. Its primary current is a vast flow of neutral hydrogen gas, the simplest and most abundant element in the universe. Each atom in this cosmic flow is a single proton orbited by a single electron, the basic building block from which everything else is forged. Drifting within this hydrogen sea are traces of heavier elements, atoms like oxygen and silicon, cosmic dust that tells a story of stellar furnaces long since extinguished. Yet to call this a river in any earthly sense is to misunderstand its true nature. The density of this material is so vanishingly low it would be considered a perfect vacuum in any laboratory on Earth. We are talking about a mere handful of atoms in a space the size of a sugar cube. A single breath you take contains more molecules than an entire cubic kilometer of this stream. Its substance is less like liquid and more like the faintest idea of a fog, a memory of matter stretched across an impossible void. The magic and the reason it matters lies in the sheer, staggering volume. When you take a gas this thin and spread it across a structure 300,000 light-years long and tens of thousands of light-years wide, the numbers become astronomical. The total mass of hydrogen in the Magellanic Stream is estimated to be many hundreds of millions of times the mass of our own Sun. locked within its ethereal currents, is enough raw material to birth billions of new stars, whole galaxies worth of potential suns and planets, all drifting in a form so diffuse we can only detect its collective whisper. So here we have a paradox of cosmic proportions, a river so empty that a spaceship flying through it would register almost nothing, yet so immense that it holds the future of entire worlds within its grasp. It is a reservoir of possibility written in the faintest ink of the cosmos, and its very existence points to a force powerful enough to sculpt something so fragile on such a monumental scale. The force that carved this river operates on a scale of both unimaginable power and delicate precision. To understand its creation, we must witness a gravitational tug-of-war playing out over billions of years. The leading theory points to two powerful cosmic processes working in concert: tidal stripping and ram pressure stripping. Picture our Milky Way not as a static island of stars, but as a dominant gravitational presence, a king in its local domain. Orbiting it are the Magellanic Clouds, two smaller dwarf galaxies that are not merely passing by, but are caught in a slow, grand orbital dance. As these satellite galaxies swing through their long paths around the Milky Way, they do not travel through empty space. They are moving through the Milky Way's own extended atmosphere, a hot, thin gas known as the galactic halo. This is where the sculpting begins. First, there is the direct pull of gravity itself, the tidal force. Just as the Moon's gravity tugs on Earth's oceans to create tides, the Milky Way's immense gravity exerts a stronger pull on the side of the Magellanic Clouds closest to it, and a weaker pull on the far side. This difference in pull stretches the galaxies, and over countless orbits, this stretching becomes a pulling. It acts like a cosmic hand, slowly but relentlessly drawing out tendrils of gas from the dwarfs, not in a single violent rip, but in a continuous, graceful unraveling. This is tidal stripping, the primary force that likely provided the initial thread of the stream. But gravity is only part of the story. As the Magellanic Clouds plow through the Milky Way's halo at fantastic speeds, they face a second, more abrasive force: ram pressure. Imagine sticking your hand out of the window of a fast-moving car. The rush of air pushes against your palm, and if you were holding a handful of fine dust, the wind would strip it away from you. The hot gas of the galactic halo acts as that cosmic wind. As the dwarf galaxies move, this halo gas rams into their own gas clouds, creating a pressure that can overcome the dwarf's weaker gravity and literally blow the gas out into space. This process, ram pressure stripping, further scours material from the clouds, feeding it into the growing river. Together, these forces create the phenomenon we see. Tidal forces provide the long, stretching pull, drawing the gas out into a filament. Ram pressure provides the push, helping to strip the gas free and shape its flow. The result is not a chaotic explosion, but a surprisingly coherent river, a billion-year testament to a gentle, persistent theft of matter by a giant from its smaller companions. This elegant explanation, however, would soon confront a puzzling contradiction, one that pointed to a missing piece in the cosmic equation. Yet this elegant theory of gentle tides soon faced a glaring problem. The river had a shape that gravity alone could not explain. When astronomers mapped the Magellanic Stream in greater detail, they discovered it was not one simple ribbon flowing behind the dwarf galaxies. It had a peculiar, forked structure. There was the immense, sweeping arc we've been discussing, which trails behind the Magellanic Clouds as they orbit. But there was also another, smaller filament, a branch of gas that was not behind the clouds but ahead of them in their orbital path. This feature was named the leading arm. Think of a comet soaring through the solar system. As it travels, the pressure of the solar wind and radiation blows gas and dust away from the sun, creating a long, beautiful tail that always points away from the star's light. That tail is purely a trailing feature. Now, imagine if that comet also had a second, smaller tail pointing ahead of it in the direction it's flying. That would be bizarre, and it would immediately tell you that something more complicated is happening than just solar wind. The leading arm is exactly that, a cosmic contradiction. According to simple tidal and ram pressure models, all the stripped gas should be left behind, forming a tail in the wake of the moving galaxies, just like a comet's tail. Gravity pulls from behind, and the galactic wind blows from the front, so the debris should all end up in the rear. The presence of gas ahead of the clouds was like finding evidence at a crime scene that the victim was in two places at once. It pointed to an additional actor, a hidden force with the power to pull material not just backward but forward as well. This bifurcated structure, the leading arm and the trailing stream, became the key forensic evidence. It told astronomers that the story they had written was incomplete. The river was not merely a product of the Milky Way's gravity acting on two passive dwarfs. The Magellanic Clouds themselves were interacting with each other in a violent, dynamic dance long before they ever approached our galaxy, and that ancient drama left its signature in the gas. To solve the mystery of the forward-pointing arm, scientists had to look deeper into the past, reconstructing a celestial history where the two small galaxies were not peaceful companions, but engaged in a gravitational clash that would set the stage for everything we see today. The mystery of the forward-pointing arm demanded a new kind of evidence, a detailed map of the river itself. To chart its course, astronomers turned to the most powerful eyes in the sky, both in space and on the ground. The Hubble Space Telescope, along with giant radio observatories like the Green Bank Telescope and the Atacama Large Millimeter Array, began a meticulous survey. They did not take pictures in visible light, for the stream is too faint and cold to glow that way. Instead, they listened. These instruments detect the faint radio whispers of hydrogen atoms or the subtle absorption of ultraviolet light from distant quasars as it passes through the stream's gas. This allowed them to do something remarkable: construct a three-dimensional velocity map. They could not only see where the gas was, but also precisely how fast and in what direction every part of it was moving. The resulting map was a revelation. It showed the stream was far more than a smooth, simple ribbon. Embedded within its vast flow were distinct clumps and clouds, denser knots of gas like boulders in a riverbed. More importantly, the velocity data painted a clear picture of two separate currents. One flowed in a coherent arc behind the Magellanic Clouds, the classic trailing stream. The other, the leading arm, was a separate, faster-moving filament surging ahead of them. This bifurcated structure was now an undeniable fact, a fork in the cosmic road. The data showed these two arms were not just offset in space, but also in motion, telling different parts of a much more complex history. Finding the clumps was one thing, but measuring their precise motion was the key. The velocity maps revealed the gas was not all falling smoothly toward the Milky Way. Some sections were moving surprisingly fast, others were almost stagnant, and the leading and trailing portions had distinct kinematic signatures, like two different rivers flowing into the same ocean but from separate mountain ranges. This complexity was the final nail in the coffin for the simple tidal model. A single gravitational interaction with the Milky Way could not produce two such distinct, coherent structures moving in opposite directions relative to the clouds. The river's intricate anatomy proved its origin story was not a simple tale of theft by a giant, but a layered epic with multiple chapters. The very maps meant to clarify its path had instead deepened the mystery, forcing scientists to look beyond our galaxy and into a turbulent past where two small galaxies collided long before they ever entered our neighborhood. The velocity maps created a new and even deeper puzzle. When astronomers fed all this beautiful, complex data into supercomputer simulations, attempting to rewind the cosmic clock and replay the birth of the stream, the models kept failing. They programmed in the known masses of the Milky Way and the Magellanic Clouds the laws of gravity as we understand them and set the celestial dance in motion. But the virtual universe refused to cooperate. No matter how they tweaked the starting conditions, the simulated streams were always wrong. They were too short or contained far too little gas or appeared in the wrong place entirely compared to the majestic, sprawling river we actually observed. The math was clear and it was shocking. Based on their visible stars and gas, the Magellanic Clouds simply did not have enough gravitational muscle to hold onto such vast amounts of material for so long, nor to have it stripped in such a coherent, massive filament. The sheer scale of the river demanded a source of gravity that was not present in the equations. It was as if you tried to simulate the erosion of a mountain into a Grand Canyon, but your model only included a small hill. The canyon could not exist without a much larger mountain present in the past. This was the missing mass problem, a glaring gap between prediction and reality. The simulations pointed to only two possible, equally profound conclusions. Either our fundamental understanding of gravity itself was incomplete on these galactic scales, a radical idea that some scientists explored, or there was something else adding immense, unseen weight to the Magellanic Clouds, a hidden source of gravity that once bound the gas tightly before it was stolen away. This second possibility led directly to one of the most important and mysterious concepts in modern cosmology, dark matter halos. We now believe that every galaxy, big or small, is not just its visible stars and gas. It is embedded within a vast, spherical cloud of invisible matter, a halo that extends far beyond the glowing disk we see. This dark matter does not emit, absorb, or reflect light, hence its name. We cannot see it with any telescope, but we can feel its gravitational grip. It is the hidden scaffolding of the universe, the unseen framework that dictates how galaxies form and move. The failed simulations strongly suggested that long ago, the Magellanic Clouds were not the relatively bare dwarfs we see today. They were once shrouded in massive, dense halos of this dark matter, making them gravitationally obese. These halos acted like deep gravitational wells, allowing the clouds to hold onto enormous reservoirs of gas for billions of years. Then, when they finally ventured too close to the even more massive halo of the Milky Way, that gas was not just loosely blown away. It was violently and coherently ripped from a powerful anchor, creating the immense structured river we detect. The Magellanic Stream, therefore, is more than a river of gas. It is a fossil imprint, a ghostly silhouette of something that is no longer there. Its very existence and form are a historical record of those ancient, invisible halos. By studying the river's twists and turns, we are not just looking at hydrogen, we are reading the faded handwriting of dark matter itself, deciphering how it shaped a cosmic drama that began long before our solar system even existed. The river's immense scale is a direct measurement of something we cannot see. To account for the sheer mass and elegant structure of the Magellanic Stream, astronomers realized the Magellanic Clouds could not have been ordinary collections of stars and gas. They must have been, and to some extent still are, embedded within colossal spheres of dark matter. This invisible substance forms a deep gravitational well around each dwarf galaxy, a hidden anchor that holds everything together. Think of it this way: if the visible galaxy is a city of glowing lights, the dark matter halo is the entire continent upon which that city is built. It is far larger, far more massive, and provides the foundational gravity that defines the galaxy's true shape and strength. Without these massive halos, the clouds would have been like sandcastles at high tide, easily dissolved by the Milky Way's gravity long ago, leaving behind only a faint, disorganized puff of gas instead of a coherent river hundreds of thousands of light-years long. The dark matter provided the necessary weight, the gravitational muscle to hold onto vast gas reserves for billions of years. Then, when the tidal forces of the Milky Way finally did pull that gas away, the dark matter halo acted like a heavy root system. It wasn't just loose topsoil blowing away, it was a deep layer of earth being slowly torn from a massive anchor. This violent, rooted extraction is what gave the stream its remarkable length and density, sculpting it into the filament we observe rather than a dispersed cloud. In this way, the Magellanic Stream is not merely a curiosity. It is one of the cleanest pieces of evidence we have for the existence and dominant influence of dark matter on galactic scales. We are not inferring dark matter from subtle mathematical discrepancies alone. We are looking at its handiwork, a fossil river carved by the gravity of invisible giants. The stream's very existence, its mass, and its shape are a historical record written in hydrogen, telling us that what we see in the universe is only a fraction of the story. The true architects of cosmic structure are these unseen halos, and the river flowing through space is their lasting signature. But a river is not defined by its water alone, it is defined by its state. The Magellanic Stream held another surprise, one that revealed it was not a cold, dark ribbon, but a river of many colors glowing with a hidden light. As astronomers trained more sensitive instruments on it, they discovered that significant portions of the stream were not neutral hydrogen at all. The atoms had been ionized, stripped of their electrons, causing the gas to emit a faint, ghostly glow in ultraviolet wavelength. This was a crucial clue because ionization requires energy, a lot of it. Something was actively cooking the stream, heating it up and tearing electrons from their atoms across vast distances. The question became, what cosmic furnace was providing the heat? Several suspects emerged. The first was the ambient ultraviolet background radiation that fills the entire universe, the leftover glow from countless quasars and galaxies over cosmic time. This pervasive light could slowly ionize the gas like a weak but constant sun shining on a fog. The second suspect was much closer to home, the Milky Way itself. Our galaxy is not quiet, it is a churning engine of star formation, and young, massive stars flood space with intense ultraviolet radiation. Could this local light be bathing the nearer parts of the stream, energizing it? The third possibility was more violent and internal. As the stream plows through the Milky Way's halo at tremendous speeds, the gas might be experiencing immense shocks. Think of a sonic boom, but on a galactic scale, where the leading edge of the stream compresses and heats the gas it rams into, or where different currents within the stream collide with each other. These shocks could provide a tremendous, localized source of energy, ionizing the gas from within. The truth, as it often is in cosmic forensics, appears to be a combination of all these factors. Different segments of the river glow for different reasons. Parts closer to the Milky Way likely feel the heat of our galaxy's stellar radiation. Other sections, particularly where the gas shows signs of turbulence and clumping, might be illuminated by internal shocks. And throughout it all, the soft background hum of the universe provides a base level of ionization. This layered state transforms our understanding of the stream from a passive fossil into a dynamic, evolving structure. It is not simply drifting, it is interacting, being shaped and heated by its environment even as it flows. The ionization is like seeing steam rise from a cold river on a winter morning, a visible sign of an energetic exchange between the water and the air. That faint ultraviolet glow is a testament to a river under pressure, a celestial structure caught in the crossfire of cosmic forces, and its changing colors tell us the story of its journey. This river has a final destination, and it is headed straight for home. The Magellanic Stream is not aimlessly drifting through the void. It is on a precise billion-year collision course with the disk of our own Milky Way galaxy. Under the relentless pull of our galaxy's gravity, the entire immense structure is falling inward, its countless atoms accelerating toward the bright band of stars we see in our night sky. In cosmic terms, the river is already beginning to pour over the edge of the galactic disk, a silent, invisible rain of primordial material starting its long descent. So what happens when this river finally reaches the sea? The fate of this gas is a story of cosmic recycling on the grandest scale imaginable. As the leading tendrils of the stream plunge into the thicker regions of our galaxy's outer disk, they will encounter resistance. The gas will compress, it will shock, and it will begin to mix with the Milky Way's own interstellar medium. This process is not a violent explosion, but a gradual, transformative merger. The cold, diffuse hydrogen of the stream will pile up, becoming denser and denser under its own gravity and the pressure of its new environment. And in the dense, cold clouds of space, magic happens. When a cloud of gas reaches a critical density, pockets within it can collapse under their own weight. These collapsing knots become nurseries for new stars. The pristine hydrogen from the Magellanic Stream, possibly enriched with those traces of heavier elements we detected, will become the raw fuel for future stellar furnaces. In this way, the river completes an epic cycle. It began as part of the gaseous reservoirs of two small satellite galaxies. It was stolen away over eons, stretched into a filament hundreds of thousands of light years long, and now it is returning to a larger galactic home. The material that once might have formed stars in the Magellanic Clouds is instead destined to ignite within the spiral arms of the Milky Way. This makes the stream a vital source of intergalactic recycling, a delivery system of fresh gas that can replenish our galaxy's star-forming reserves. Our Milky Way, like all large galaxies, is slowly using up its available gas as it forms stars. Without new inflows, star formation would eventually sputter and cease. The Magellanic Stream represents one of the largest known sources of such incoming fuel. It directly connects the past and future of our local galactic neighborhood, showing that galaxies are not isolated islands but interactive ecosystems. The gas raining down from this river could one day be part of a new planetary system, perhaps even one that cradles life. So the next time you look up at the Milky Way, remember you are not just looking at a static tapestry of stars. You are witnessing a dynamic, evolving structure, one that is being actively fed by a river in space, a river whose ancient currents are writing the next chapter in our galaxy's story. But this grand story of theft and delivery is not unique to our galactic neighborhood. The Milky Way is not the only giant with a taste for the gas of its smaller companions. Across the vast gulf of intergalactic space, astronomers have begun to find rivers everywhere they look. Our own Magellanic Stream is simply the closest and clearest example, a textbook page we can read in high definition. Venture 2.5 million light-years away to our nearest large galactic neighbor, the Andromeda Galaxy, and you will find a similar drama unfolding. Andromeda, which is even larger than the Milky Way, is also surrounded by a complex web of gaseous filaments. Hubble's Space Telescope observations have revealed massive streams of hydrogen gas, some containing over 100 million suns worth of material, swirling around Andromeda and connecting it to its own retinue of dwarf galaxies. These are not random clouds, they are the torn-apart remnants of smaller systems, the cosmic rivers feeding a different giant. Look even farther into the heart of immense galaxy clusters like Virgo, and the scale becomes almost unimaginable. Here, in a crowded metropolis of thousands of galaxies, the rivers are not just between a giant and its satellites, but between the giants themselves. Enormous filaments of hot, ionized gas detected by X-ray telescopes stretch for millions of light-years between the cluster's most massive galaxies. This is intergalactic plumbing on the grandest scale, a network of superheated rivers flowing through the dark matter scaffolding of the universe itself, redistributing material and energy on a truly cosmic stage. What this tells us is profoundly important. The process that created our Magellanic Stream is a universal one. It is a fundamental mechanism of how galaxies interact, grow, and evolve over billions of years. Gravity is the great sculptor, and dark matter is the hidden framework, and together they are constantly weaving and reweaving the visible fabric of the cosmos with these immense flowing threads. Our local river is a gift, a nearby laboratory where we can study this universal process in exquisite detail. By understanding its currents, its composition, and its fate, we are learning the language of galactic evolution spoken across the entire universe. Every one of those distant streams is telling a similar story of attraction, disruption, and renewal, a story that began with the first galaxies and will continue until the last stars fade. But the cosmic river may have already sent a smaller current ahead as a warning. Drifting toward us at nearly 200 miles per second is another enigmatic structure known as the Smith Cloud. This is not a distant filament, but a massive, high-velocity cloud of hydrogen gas located right on our galactic doorstep, just 15,000 light-years from the Milky Way's disk. It is enormous, stretching over 10,000 light-years long, and it is on a direct collision course with our galaxy's spiral arm. In many ways, it looks like a smaller, more isolated version of the Magellanic Stream, a solitary river of gas plunging toward a larger sea. This striking similarity immediately sparked a profound question. Is the Smith Cloud a piece of the great stream that broke off long ago, a tributary that raced ahead of the main flow? Or is it something else entirely, perhaps the shredded remnant of a failed dwarf galaxy that never quite managed to form stars? The answer lies in its chemical fingerprint. When astronomers analyzed the light from stars shining behind the Smith Cloud, they found a crucial clue. Its gas contains heavier elements like sulfur and oxygen. This is significant because pristine gas from the empty void between galaxies, gas that has never been inside a star-forming galaxy, should be almost pure hydrogen and helium. The presence of these heavier elements forged in stellar furnaces means the Smith Cloud's material has been processed before. It has lived a previous life inside a galaxy. This evidence points strongly toward an origin linked to the Magellanic System. The chemical signature of the Smith Cloud's gas is a remarkably close match to that found in the large Magellanic Cloud. It is as if we found a distinctive rock downstream and matched its mineral composition to a specific mountain upstream. The leading theory now suggests the Smith Cloud is indeed a fragment, a massive splinter of gas that was torn from the Magellanic Clouds even earlier than the main stream, perhaps during a close encounter between the two dwarfs billions of years ago. This fragment, given a different gravitational kick, shot out ahead on its own unique trajectory, becoming a solitary scout from the same ancient event. By studying this cloud in incredible detail, we get a preview of the main stream's ultimate fate. We can watch, in a kind of cosmic time-lapse, exactly how a river of extragalactic gas merges with the Milky Way. Observations show the Smith Cloud is already beginning to disintegrate as it encounters the outer fringes of our galaxy's halo. Its leading edge is glowing, heated and ionized by the pressure of this new environment, and a faint tail of gas is being stripped away behind it, like the wake of a boat entering a harbor. In this way, the Smith Cloud acts as a perfect natural laboratory. It is a smaller, simpler test case happening right now, showing us the physics of accretion, the process of a galaxy feeding. It demonstrates how these massive flows are shredded, heated, and eventually assimilated, their gas cooling and settling into the galactic disk to fuel future generations of stars. So this mysterious cloud is more than just a celestial curiosity. It is a tributary joining a larger river, offering us a front-row seat to the silent, majestic, and ongoing construction of our galactic home. For decades, the story of the river was built on a shaky foundation, an assumption about where its source began its journey. The true motion of the Magellanic Clouds through space was surprisingly uncertain. We could see where they were, but pinning down their precise speed and direction, the vectors needed to rewind the cosmic clock, was like trying to map a car's exact route using only a few blurry snapshots. All our models of the stream's birth depended on this critical starting point, and if it was wrong, everything that followed would be wrong too. This fundamental uncertainty changed with a silent revolution happening 500,000 miles from Earth. The European Space Agency's Gaia Space Observatory is not a telescope that takes pretty pictures of nebulae. it is a celestial cartographer of staggering ambition and precision. Since its launch, Gaia has been performing the largest and most detailed stellar census in history, measuring the positions, distances, and motions of over 1 billion stars in our galaxy with mind-boggling accuracy. It is creating a three-dimensional, dynamic map of the Milky Way, but its gaze extends beyond our own stars. Gaia has also locked onto millions of individual stars within the large and small Magellanic Clouds themselves. By tracking the subtle, collective motion of these stars against the more distant background of the cosmos, Gaia has done what was previously impossible. It has given us the precise velocity and trajectory of the dwarf galaxies themselves, not as fuzzy blobs, but as distinct swarms of stars moving through the void. This data is like finding the original flight recorder from a long-ago plane crash. It allows astronomers to recalculate the orbits of the Magellanic Clouds with confidence, tracing their paths backward and forward through time with a clarity we never had before. The new trajectories were a revelation. They showed the clouds are moving faster and on a more tangential path around the Milky Way than earlier, cruder estimates had suggested. They are not on a simple, doomed plunge into the heart of our galaxy, but on a more grazing, elongated orbit. This single correction changes everything about the stream's formation story. When you feed Gaia's precise orbital data into the supercomputer simulations, the models begin to behave. The timing of interactions shifts, the gravitational tugs align differently, and suddenly, the simulations start to produce streams that look remarkably like the one we actually see in the sky. The mass discrepancy, the puzzle of the missing gravity, begins to resolve. The new orbits imply the clouds experienced a closer, more dramatic encounter with the Milky Way in the relatively recent past, perhaps 1 to 2 billion years ago. This closer pass would have exerted far stronger tidal forces, enough to violently strip gas from galaxies that were, according to the new models, still robustly anchored by their massive dark matter halos. The river we see is the direct result of that specific, timed gravitational shock. Gaia's data is thus doing more than just refining a map. It is providing the key empirical evidence that confirms the entire theoretical framework. The precise motions validate the need for those massive, invisible dark matter halos to explain the stream's scale and coherence. They turn a compelling hypothesis into a strongly supported narrative. We are no longer guessing at the past based on a blurry present. We are reading it from a precise record written in the motions of a billion suns. This revolution in measurement is quietly confirming that the grandest structures in our sky are born from the interplay between what we see and what we must infer, between the glittering stars and the dark, shaping hands they cannot escape. Yet there is another story, one far more dramatic and immediate. Some astronomers argue the river was not born from a slow, billion-year theft, but in a single, shattering cosmic collision. This alternative theory proposes that hundreds of millions of years ago, the large and small Magellanic Clouds did not merely dance around each other, they crashed directly together. In this violent merger scenario, the titanic gravitational forces of such an impact would have been catastrophic. Enormous tsunamis of gas, not gentle tidal tendrils, would have been blasted out from both galaxies, flung into the void in opposing directions. This single, explosive event could have created both the trailing stream and the leading arm in one fell swoop, as material was ejected forward and backward from the point of impact like debris from a colossal detonation. The evidence for this lies in the present state of the clouds themselves. Observations reveal their gaseous structures are profoundly disturbed, warped, and stretched in ways that suggest a recent and violent encounter, not just a slow gravitational waltz. There is a vast bridge of gas connecting the two dwarfs, and the small Magellanic Cloud appears torn and distorted, as if it is still reeling from a tremendous blow. This merger theory elegantly solves the puzzle of the leading arm, something the gradual tidal model struggled with. A direct collision naturally throws material in all directions, providing a straightforward mechanism for gas to end up both ahead of and behind the system's motion. It frames the Magellanic Stream not as a slowly unraveling thread, but as the scattered aftermath of a galactic car crash, a fossilized shockwave frozen in space. This idea fundamentally challenges the patient narrative of tidal stripping. It suggests the river is not a product of persistent erosion, but of a singular, defining catastrophe. The debate between these two models, the gradualist and the catastrophist, is not merely academic. It forces us to ask a deeper question about the nature of cosmic history. Do the largest structures form through the relentless accumulation of tiny forces over eons, or are they shaped in sudden, violent moments that reset the clock? The river holds the answer, but its currents whisper two very different tales of origin. The river's chemistry holds a clue that complicates its entire origin story. When scientists finally managed to analyze the elemental makeup of the Magellanic Stream, they expected to find something simple. Since it came from small, dwarf galaxies, which are typically poor in heavy elements, the gas should have been relatively pristine, composed almost entirely of hydrogen and helium with only trace amounts of anything else. But the data told a different tale. Spectroscopic readings, which act like a cosmic barcode scanner, revealed the stream's gas contains a surprising abundance of heavier elements like oxygen and sulfur. These are elements astronomers often call metals, forged in the hearts of massive stars and scattered into space by supernova explosions. The presence of these metals in significant quantities was a genuine puzzle. It meant this material was not untouched primordial hydrogen from the cosmic dawn. It had been processed, enriched by a previous generation of stars. This chemical fingerprint forced a difficult question: where did this enriched gas come from? One possibility is that the river was drawn from the very hearts of the Magellanic Clouds. Galaxies are not chemically uniform, they have gradients. The inner regions where stars have formed and died in cycles for billions of years are metal-rich factories. The outer fringes are more pristine. If the tidal forces that created the stream reached deep into the dwarf's central regions, they could have pulled out this enriched material, like dredging up mud from the bottom of a lake instead of skimming clear water from the surface. This would imply a far more violent and penetrating gravitational interaction than we previously considered. The other, equally intriguing possibility is pollution. As the stream snakes its way toward us, it is not moving through a perfect vacuum. It is flowing through the Milky Way's own extended gaseous halo, a reservoir of hot, metal-enriched material that has been blown out of our galaxy by countless supernovae over its lifetime. Could the stream be picking up these heavier elements along the way, like a river flowing through a mineral-rich landscape, gradually changing its composition? This would mean the river is not a closed fossil, but an interactive structure, actively mixing with its environment and being chemically altered during its long journey. Each explanation points to a radically different history. If the metals are native to the stream, it tells us the Magellanic Clouds were more chemically evolved and their inner regions were more violently disrupted than our models predicted. If the metals are acquired from our halo, it reveals the stream is a dynamic participant in a larger galactic ecosystem, exchanging material as it flows. This single chemical clue, this unexpected fingerprint of oxygen and sulfur, therefore does more than just describe what the river is made of. It challenges us to refine the entire narrative of its birth and journey, forcing us to decide if we are looking at a relic of a distant catastrophe or an active thread being woven into the fabric of our galaxy in real time. The river's journey is far from over. Its final chapters are still being written in the silent dark of the future. Supercomputer simulations, now armed with precise data, allow us to project this cosmic story forward billions of years. What they reveal is a slow, majestic, and inevitable conclusion. The Magellanic Stream will not simply fall into the Milky Way in a single splash. Instead, drawn by our galaxy's immense gravity, the entire filament will continue to curl around us like a great celestial serpent coiling around its prey. Over the next several billion years, the river's leading sections will complete their plunge into the galactic disk, while the vast trailing end, still connected to the Magellanic Clouds themselves, will swing around in a grand arc, eventually wrapping itself around the Milky Way's circumference. This is not a quick process, it is a patient gravitational dance measured in eons. As the stream wraps, it will encounter increasing turbulence. The differing speeds of its various segments, combined with the churning motion of the Milky Way's own gas, will cause the once coherent ribbon to fracture. It will shear apart into immense, tumbling clouds and diffuse filaments, its identity slowly dissolving as it mixes with the richer, denser interstellar medium of our galaxy. Imagine pouring a thin stream of cream into a swirling cup of coffee. At first, you can see the distinct ribbon of white winding through the dark liquid, but slowly, through motion and diffusion, the two substances blend until they become one. The Magellanic Stream is that cream, and the Milky Way is the coffee, engaged in a mixing process that spans cosmic ages. The gas from the river will lose its unique signature, its atoms becoming indistinguishable from the native gas of our galactic disk. It will settle into the spiral arms, cooling and pooling within vast molecular clouds. And here lies the true finale of this epic story, a burst of new creation. This incoming infusion of fresh, albeit slightly enriched, hydrogen fuel is precisely what our galaxy needs to reignite its stellar engines in the distant future. Billions of years from now, long after the stream itself has vanished from the sky, the material that once flowed between galaxies will collapse under its own gravity. Within those dark, cold nurseries, new stars will flicker to life. Some will be modest yellow suns like our own, others will be brilliant blue giants that live fast and die young. Around them, planets may coalesce from the accompanying dust. This river, born from a clash of dwarfs and shaped by dark matter, will have completed its ultimate purpose, recycling its primordial substance into the raw materials for new solar systems and perhaps new possibilities. The silent river in space, a fossil of the past, is therefore also a blueprint for the future, a delivery of stellar destiny that will one day light up the Milky Way with suns that do not yet exist. This silent river offers more than a story, it is a cosmic proving ground. The immense, simple structure of the Magellanic Stream presents scientists with a unique natural laboratory, one of the cleanest in the universe for testing the most fundamental laws of physics. Here, in this low-density environment far from the crowded chaos of galactic centers, we can ask a profound question: does gravity work exactly as we think it does on these colossal scales? The stream allows for a direct test between two competing visions of the cosmos. On one side is the prevailing dark matter model, which says the stream's existence and shape are best explained by the gravitational pull of invisible halos. On the other is an alternative theory called modified Newtonian dynamics, often abbreviated to MOND. This idea proposes that we do not need invisible matter. Instead, our understanding of gravity itself is incomplete, and its force behaves differently in the extremely weak gravitational fields found at the outskirts of galaxies and in structures like the stream. The Magellanic Stream is a perfect test case for this debate. Its gas is so diffuse and it moves through such a quiet region of space that the gravitational forces at play are exceptionally feeble. According to MOND, in these weak field environments, gravity should exhibit a subtle boost, a modification that could explain the motions we see without invoking dark matter. By mapping the stream's precise kinematics, the exact speed and direction of every clump of gas, and comparing it to predictions from both the dark matter and MOND models, astronomers can perform a crucial experiment. The river becomes a ruler against which we can measure the very law that binds the universe together. Early results from this ongoing experiment are intriguing. The detailed motion maps from observatories like Gaia seem to align more strongly with simulations that include massive dark matter halos around the Magellanic Clouds. The stream's specific structure and the orbits of the clouds themselves appear difficult for MOND to explain without additional, complex assumptions. But the investigation goes deeper, probing not just if dark matter exists, but what it is. The stream's behavior might also reveal secrets about the nature of dark matter particles themselves. Is dark matter cold, meaning its particles move slowly, allowing it to clump easily and form the dense halos we infer? Or is it warm, with faster-moving particles that would create smoother, more spread-out halos? These different personalities would leave distinct imprints on a structure like the Magellanic Stream. A cold, dark matter halo would be very effective at gravitationally sculpting a long, coherent filament as we see. A warm dark matter halo might produce a stream that is more fragmented or that formed differently. By refining our measurements of the stream's density, its clumpiness, and its exact history, we are essentially taking the temperature of the invisible universe. This river, therefore, is not just an object of study, it is an instrument. It is a natural accelerator, a detector built on a galactic scale, silently conducting experiments that our most powerful particle colliders on Earth cannot yet perform. Every new observation of its faint light is day to point in the greatest detective story of all, one where the clues are written in the motion of hydrogen and the suspect is the hidden majority of the cosmos. Yet for all its immense mass of potential star stuff, the river flows through the void in profound silence and darkness. Here lies one of its most puzzling contradictions. Within this colossal reservoir of gas, enough to spawn billions of suns, astronomers have searched in vain for the telltale glow of newborn stars. The Magellanic Stream appears to be almost completely barren, a river of pure potential that has never sparked into stellar fire. This absence is not just curious, it is a vital clue to the conditions needed for creation itself. Star formation is a delicate and demanding process. It requires more than just a large amount of gas. It requires that gas to reach a critical state of density and coldness. Imagine trying to start a fire with a massive, damp log. You have plenty of fuel, but it is spread out and unsuitable for a spark to catch. The gas in the stream is like that, extraordinarily diffuse. Its atoms are so widely spaced that the gravitational pull they exert on each other is incredibly weak, too weak to overcome the natural pressure and turbulence that keeps them apart. There are no dense, cold knots or cores within the stream where gravity can decisively win the battle and begin a collapse. The environment itself works against it. The stream is also bathed in external energy, the same ultraviolet radiation from the Milky Way and the cosmic background that ionizes parts of the gas also acts to heat it. Warm gas is energetic and resistant to collapsing. Furthermore, magnetic fields woven through the stream like invisible threads can provide a supporting pressure, propping the gas up against its own weight. Turbulence from the stream's motion and its interaction with the galactic halo stirs the material, keeping it from settling into the quiet, dense pockets required for star birth. This makes the Magellanic Stream a cosmic example of arrested development, a vast collection of pristine material preserved in a state of perpetual readiness. It is a fossil, but a fossil of potential, not of past activity. In this way, the river offers a unique control experiment. By studying it, we learn what factors prevent stars from forming, just as much as we learn what allows them to ignite. It shows us that having the raw ingredients is only the first step. The universe also needs the right recipe of density, cold, and quiet to turn those ingredients into suns. The stream's enduring darkness is a silent testament to the precise and fragile conditions required to light a candle in the cosmic night. The river's story is not an isolated chapter, but a single page in the universe's grand biography of growth. This immense filament of gas is a direct, observable snapshot of a process so fundamental it shaped the cosmos as we know it, hierarchical structure formation. The idea is both simple and profound. The universe builds from the bottom up. Small things merge to form larger things. In the earliest epochs, tiny fluctuations in the dense, hot soup of the Big Bang grew under gravity, pulling in gas to form the first stars and star clusters. These then gathered into dwarf galaxies, and over billions of years, these dwarfs were drawn together by their mutual gravity, colliding and merging to build ever larger galaxies. Our majestic Milky Way, with its hundreds of billions of stars, was not born this grand. It was assembled piece by piece from countless smaller galactic building blocks over an almost unimaginable span of time. For decades, this was a compelling theory supported by computer simulations and the fossil record of stars in our galaxy's halo. But it was a story of the distant past, a faded archaeological dig. The Magellanic Stream changes that. It is not a fossil of a completed merger, but live, ongoing evidence. We are witnessing the process in its intermediate stage, a crucial phase between first encounter and final assimilation. The river is the cosmic umbilical cord, still attached, actively transferring material from the smaller satellites to the larger host. It shows us that galaxy growth is not a series of ancient, catastrophic collisions alone, but also a continuous, gentle feeding, a slow accretion of gas that can fuel star formation for eons. This changes our perspective entirely. We are not just looking at a river in space, we are watching our galaxy eat. We are seeing the Milky Way in real cosmic time, actively consuming and digesting the raw material from its companions to sustain itself and grow larger. Every atom flowing down that filament is a testament to a dynamic, evolving universe, one where galaxies are not static islands but living, breathing entities in a constant state of becoming. The stream proves that the hierarchical model is not just a story of the past, it is the ongoing reality of our galactic neighborhood, and we have a front row seat to the feast. The breathtaking images of the Magellanic Stream are not photographs in any conventional sense. They are maps of the invisible, painstakingly translated from the language of physics into a form our eyes can understand. The raw data arrives not as light, but as numbers, a torrent of coordinates and intensity values collected by massive radio telescopes like the Green Bank Telescope or the Parkes Observatory. These instruments are tuned to listen for a specific, faint radio whisper, the 21-centimeter emission line of neutral hydrogen. As hydrogen atoms drift through space, a subtle shift in the spin of the electron relative to the proton causes them to emit this signature radio wave. By meticulously scanning the sky, astronomers build a three-dimensional data cube, plotting where this emission is strongest and measuring its Doppler shift to determine the gas's velocity toward or away from us. The result is a colossal, ghostly point cloud, a digital constellation of measurements where each point represents a pocket of hydrogen in a specific location, moving at a specific speed. This raw data cube is the unadorned truth of the river, a scientific ledger of its existence. But to see its shape, to grasp its majesty, requires an act of creative translation. Data visualization specialists take this three-dimensional point cloud and begin a process akin to sculpting with light. They assign colors not arbitrarily but with scientific intent. Often, velocity becomes the palette. Gas moving toward us might be shaded in cool blues, while gas moving away shifts into warm reds and oranges, creating a thermal map of motion. Density is represented by brightness, with thicker clumps of gas glowing more intensely than the tenuous filaments. The final, graceful ribbon that arcs across planetarium domes is an isosurface, a digital shell drawn to enclose the regions where the hydrogen signal passes a certain threshold. The artist must decide where to draw that threshold, balancing the need to show the stream's full, wispy extent against the clutter of background noise. This is where hard science and informed artistry blend. The colors are chosen for clarity and contrast. The viewing angle is selected to reveal the most informative structure, and the surrounding star field is often added for cosmic context. Every beautiful visualization you see is therefore a careful argument, a hypothesis made visible. It is a bridge between the abstract mathematics of astrophysics and the human need to see and comprehend. These images do not show the stream as it would appear to our eyes, for our eyes would see nothing at all. Instead, they reveal the stream as it exists in the mind of science, a river of data given form, allowing us to navigate a reality that is otherwise forever hidden in the dark. That same human instinct to see rivers in the stars has been with us since the dawn of civilization. For thousands of years, our ancestors looked up at the shimmering band arching across the night sky and saw a celestial river. The ancient Greeks named it Galaxias Kuklos, the Milky Circle, a name born from the myth of the goddess Hera's spilled milk. In Japan, it was the heavenly river Amenagawa. To the Vikings, it was the path to Valhalla. Across cultures, that luminous streak was never just a random scattering of stars. It was a flowing pathway, a source of divine nourishment, a story written in light. We have always projected the most vital features of our world onto the heavens, turning patterns into legends. The Nile, the Ganges, the Tigris and Euphrates, these were not merely waterways on Earth. They were the arteries of empires, the bringers of life and fertility, the physical manifestations of gods and goddesses. A river on the ground meant survival, connection, and destiny. It is no wonder that when we looked up, we saw the same essential shape and gave it the same profound meaning. The Milky Way was our original river in space, a mythological one. Today, we have discovered a new one, not made of myth but of cold, hard science, a river of hydrogen flowing from galaxy to galaxy. Yet in a profound way, the Magellanic Stream is a direct descendant of those ancient stories. It is a modern myth, written not by poets but by the laws of physics, yet it fulfills the same human need. We still look at the cosmos and seek the patterns, the connections, the narratives. Only now, the story is told in the language of gravity, dark matter, and galactic evolution. This river does not carry water, but the potential for new suns and worlds. It is not a path for spirits, but a pipeline of cosmic material. The parallels are deep and resonant. Just as the Nile's annual flood brought fertile silt to renew the land, this silent river brings fresh gas to renew our galaxy, feeding future star formation. Just as earthly rivers connect distant landscapes into a single system, this cosmic river connects separate galaxies into a single, interactive ecosystem. We have traded the spilled milk of a goddess for the stripped gas of dwarf galaxies, but the core idea remains: the heavens are alive with flow and connection. In identifying this structure, we are continuing humanity's oldest tradition. We are finding a story in the sky. We are simply using a new vocabulary to describe the same awe, to map a new kind of destiny written in the currents of the void. This river reminds us that science does not erase mystery. It simply gives it a new, more detailed shape, allowing the true epic of the universe to be read in its own extraordinary language. The river's story is poised to be rewritten by a new generation of eyes gazing into the dark. While our current telescopes have sketched its outline, the next decade will bring instruments of such profound power they will not just observe the Magellanic Stream, they will dive into its very heart. These observatories will shift our view from a distant map to an intimate, forensic examination, resolving mysteries that have lingered since its discovery. At the forefront is the James Webb Space Telescope. Its unparalleled infrared vision is perfectly suited to pierce through cosmic dust and analyze the stream's faint chemistry. Webb can look for the specific infrared fingerprints of molecules and ionized atoms within the river, providing a detailed chemical census. This will finally answer whether the metals in the stream are native or acquired, revealing if the gas was ripped from the dwarf's inner sanctums or polluted during its journey. More than just a snapshot, Webb could track how the chemical composition changes along the stream's length, reading it like a layered history book where each chapter has a different elemental signature. But to understand the river's full anatomy, its flow and structure, we need a telescope of a different kind, one that listens. The Square Kilometre Array, or SKA, is not a single dish but a vast network of thousands of radio antennas spread across 2 continents. When complete, it will be the most sensitive radio observatory ever built, a machine designed to hear the faintest whispers of the universe. For the Magellanic Stream, the SKA will be transformative. It will map the neutral hydrogen with a resolution and sensitivity 100 times greater than anything before. Imagine moving from a blurry outline of a river on a map to a high-definition satellite image where you can see every eddy, every small tributary, and even individual boulders in the current. The SKA will reveal the stream's fine-scale structure, pinpointing thousands of previously invisible clumps and filaments. It will measure the motions within the gas with exquisite precision, allowing us to see not just how the river is moving as a whole, but how it churns and tumbles within itself. This data will be the ultimate test for our simulations, showing us exactly where the models of tidal forces, dark matter halos, or a galactic collision succeed or fail. And there is a third piece to this puzzle, a part of the spectrum we have only glimpsed. The stream's ionized gas glows brightly in ultraviolet light, but our view from Earth's surface is limited as our atmosphere blocks most UV radiation. Future large ultraviolet space telescopes, concepts now on drawing boards at space agencies, would change that. A dedicated UV observatory could create a full sky map of the stream's ionized components, showing exactly where and why the gas is heating up. It could distinguish between ionization caused by the Milky Way's radiation, internal shocks, or the cosmic background, painting a dynamic picture of the river's interaction with its environment. Together, these 3 pillars of future astronomy, infrared, radio, and ultraviolet, will attack the mystery from every angle. They will turn the stream from a monolithic object into a dynamic ecosystem, each instrument revealing a different layer of its physics and history. The data they return will not just fill in gaps, it will likely present entirely new puzzles, phenomena we cannot yet anticipate. We stand on the shore of this cosmic river, watching as new ships are prepared for launch, vessels that will sail its currents and send back reports from a frontier we have only dreamed of exploring. This river flows just beyond the edge of our sight, a hidden geography painted across the southern sky. While you cannot look up and see the Magellanic Stream with your own eyes, you can trace its ghostly path with the help of modern tools, connecting the cosmic dots between what is visible and what is known. From anywhere on Earth, you can use free planetarium software or smartphone apps to take a virtual journey. Start by locating the 2 bright, fuzzy patches that are the Magellanic Clouds, satellites of our Milky Way only visible from the southern hemisphere. In your app, find the large Magellanic Cloud near the constellations Dorado and Mensa, and the small Magellanic Cloud nestled by Tucana. Now, imagine drawing a great, graceful arc of gas connecting these 2 clouds and curving downward toward the constellation Sagittarius, which marks the center of our own galaxy. This is the approximate riverbed of the stream. Toggle on the hydrogen map or deep sky object layers in your app if available, and this theoretical line transforms into a visual reality, a faint blue or purple ribbon superimposed on the star field. You are not just looking at a simulation, you are looking at a data-driven map of the actual structure, scaled and placed exactly where science has detected it. To make this feel even more tangible, zoom out. See how this river flows in relation to the familiar plane of the Milky Way, our home galaxy's bright band of stars. Notice how the stream seems to pour into it, a silent tributary meeting a luminous sea. This simple act of visualization does something profound. It collapses the distance between abstract science and personal experience. You are not merely being told about a river in space, you are charting its course with your own hands, seeing its relationship to the constellations you may know. It turns an immense, invisible object into a place you can point to, a hidden continent on your personal map of the cosmos. The wonder is not diminished by knowing you need an app to see it. It is enhanced because you understand that the universe is full of layers, most of which are written in a light our eyes were never built to read. Even with our most powerful tools, the river guards its deepest secrets. The very features that make it a perfect laboratory also highlight the puzzles we have yet to solve. Why is its structure so elegantly forked, with one arm leading and another trailing? This fundamental split remains the core architectural mystery, the evidence that forces us to choose between a slow tidal unraveling and a single, shattering collision between the dwarf galaxies. We still do not know the precise recipe of energy that lights up its gas. Is the ionization primarily from the Milky Way's glare, from internal shocks as the river churns, or from that faint, universal background hum? Each source tells a different story about the stream's environment and its internal dynamics. The debate over its birth, violent or gradual, is not just academic quibbling. It asks whether the cosmos builds its grandest structures through patient, persistent forces or in sudden, defining catastrophes. And perhaps most profound of all, the question of dark matter. The river's scale demands it, but how much is there and what exactly is it? The stream's behavior is our best clue to the temperature and clumpiness of this invisible substance, the hidden skeleton of the universe. These are not failures of understanding, but signposts. They mark the active frontier of human curiosity. Science is not a destination where all mysteries are solved. It is a perpetual journey where each answered question peels back a layer to reveal a deeper, more fascinating puzzle beneath. The Magellanic Stream is a gift that keeps on giving, a cosmic conversation that began with a whisper in the radio static and now engages our finest minds and instruments. Its enduring enigmas assure us that the universe is still stranger, more dynamic, and more wonderfully intricate than we have yet dared to dream. From a faint whisper in the radio static to a cornerstone of modern astronomy, the journey of the Magellanic Stream is an epic of human curiosity. It began as a spectral signature, a ghostly filament that defied explanation. Through decades of observation, debate, and technological triumph, we have come to see it for what it truly is, a cosmic Rosetta Stone. This river in space decodes multiple languages of the universe at once. Its length and shape speak the language of gravity, revealing the immense, invisible pull of dark matter halos. Its chemistry tells the story of galactic violence and stellar life cycles. Its very existence narrates the hierarchical growth of galaxies, a slow-motion feast that is still ongoing. We are not just looking at a cloud of hydrogen, we are reading the autobiography of our local cosmos, written in the flowing script of intergalactic gas. This discovery fundamentally shifts our perspective. We are no longer residents of a static, isolated island universe. We live within a dynamic, interconnected ecosystem, a place where rivers of creation flow silently through the dark, where galaxies feed and grow, and where the past continuously sculpts the future. The silent river above reminds us that we are part of a grand, unfolding story far greater than our own. What do you think the next chapter of this cosmic mystery will reveal? Share your thoughts in the comments below.